Okay, again, my pleasure to introduce Ganna Kudryavteseva, who will speak to us today about relating ample and biample topological categories with Boolean restrictions.
Okay, thank you very much, Tristan. It is my pleasure to give this talk today here, and I thank Tristan for the invitation, and very happy to have an opportunity to present my work here to your group. Yes, in this talk, I'm going to relate Boolean restriction and range semigroups with ample and biample topological categories, and it will be kind of extension of classical stone duality, which Julia has presented in the pre-talk. But let's first make an introduction. So actually, ample topological groupoids are now very well-established tool in the theory of operator algebras, groupoid operator algebras, and standard algebras, right? So, and Boolean inverse semigroups can be looked at as algebraic counterparts of ample groupoids, right? And so, Boolean inverse semigroups are in duality with ample groupoids. So, I mean, one can, in all the considerations, replace topological properties of groupoids, but by purely algebraic properties of Boolean inverse semigroups. So that's why these objects are very important. And and groupoid sister algebras are very common and important. For example, graph sister algebras, higher graph sister algebras, or the analogs, purely algebraic analog like Levitt-Pass algebras and Kumjan-Pass algebras of higher graphs. So these are very important objects, and so Boolean inverse semigroups in this situation, these are like pollinization of graph inverse semigroup of higher inverse semigroups. So, well, so let me make some historical comments about this non-commutative stone dualities. Actually, Mark Lawson in 2010 published a paper about the generalization of stone duality to Boolean inverse monoids. So, and he started this direction, which I'm going to speak about. But even before him, in 2007, Pedro Rizalde published a paper where he related pseudogroups with localic et al. Categories. So pseudogroups are analogs of Boolean inverse semigroups, but their idempotents don't form Boolean algebra, but rather a frame. And so he generalized duality between frames in locales to this non-commutative setting. So he did it at the level of objects, and Mark's duality was already functorial. Well, after that, my joint work with Mark Lawson. Actually, we posed a question. So why do we need to consider groupoids? So groupoids have this involution, right? Inverse semigroups have involution, but what about if we don't have this structure? Does the duality survive? And the answer is yes. So we can replace groupoids, ample groupoids by ample categories, and objects which replace Boolean inverse semigroups are so-called Boolean restriction semigroups. So what we did with Mark, so we did it in by the generality. Actually, we did it at localic setting first, and then we specialized it to sober special duality, and then to we went to coherent setting, and then we restricted to duality to distributive semigroups and to Boolean semigroups. So that's what we did. And actually, after that, in 2021, the paper by Pocket and Garner, which is a far-reaching generalization of Lawson's and Rizalde's duality. So what they did, actually, they extended the duality to a multi-object setting. So it was first thing, and then unified various dualities. So they found the unifying approach, which embraces topological duality, localic duality, and also other dualities. But what is important for my talk today, special case of the duality, it's duality between Boolean restriction monads, very special case, and ample topological category. So here by ample topological category in my talk, I will mean topological category whose unit space is locally compact. But here we have monoids and here we have compact unit spaces. So the duality was for monoids. Well, that's good. So I will define restriction monoids in a moment, but here in introduction, I just want to mention that so we have semi-group structure and we have star operation. It's like support operation. So restriction monoids are unary monoids. They have not only multiplication, but unary support operation. Well, and then what methodology we started with this? Well, categories have domain and range maps. So these are kind of two-sided objects. So one-sided objects are put in correspondence with two-sided objects. And I wondered, I mean, why does it look a bit unbalanced, you know? So, well, domain map somehow corresponds to this star support operation. But what about range map? So somehow perhaps it's hidden here, right? So what's to do with it? How is it encoded at the algebraic side? These kinds of questions were not addressed in the work by Coquette of Gardner, and this was my motivation to do the work I'm going to present today. Also, I will replace monoids by semigroups. So I no longer consider unital and compact setting, but locally compact setting and setting of semigroups. Well, okay. I think having said that, we can go on to definitions. So now let's define restriction and range semigroups. So first of all, let me define so-called Ehresmann semigroup. So we have semigroup with unary operation star. And we say that it is Ehresmann semigroup. So provided that semigroup, of course, and the following identities hold. So x star equals to x star y star. Identity, and finally we have one more identity. It's this hold, we have what I call Ehresmann semigroup. So here I'd like to emphasize that these objects are known as right Ehresmann semigroups. There are also left Ehresmann semigroups and two-sided Ehresmann semigroups. We will come there. But from here on, I'd like to use the following terminology. This will be just Ehresmann. Dual objects. We have unary plus operation, which satisfies dual axioms. And now let me define bi-Ehresmann semigroups. So what is bi-Ehresmann semigroup? It means that with respect to this operation, it is Ehresmann, with respect to this, it's co-Ehresmann. And the two operations are connected, right? So, and we have additional axioms. So this identity is also defined. And you see, these objects are in a way left-right symmetric, right? And I call it them bi-Ehresmann semigroups. Okay. Now, we can do it already for Ehresmann semigroups and also for co-Ehresmann. I consider the following set. S, it is the set of stars of all elements. Okay. And this axiom ensures that this is commutative semigroup, and it's not difficult to see that each element is idempotent. So it is a semi-lattice, okay, commutative semigroup. And when we have a bi-Ehresmann semigroup, then these axioms ensure us that the set is the set of all classes. And these elements are called projection, and P of S is called projection semigroups. You want an example, just to motivate that these objects are very natural. Actually, the simplest example is the following. Take some set X and let B of X be a semigroup of all binary relations. Okay, so with respect to ordinary multiplication relations, star operation is the domain relation, class operation is the range relation of a given binary relation, and one sees that easy to check that these axioms are satisfied, and we have bi-Ehresmann semigroups. Now, restriction semigroups. With multiplication and unary operation star, it's called a restriction semigroup. It is Ehresmann. And in addition to that, we have the following axiom. I mean, which in fact is an identity. So whenever you have X star Y, so remember that this is a projection, right? And we can move this projection to the right of Y. So it is Y. So dually we can divide two restrictions in a group. And by restriction, it's a bi-Ehresmann semigroup, which is restriction and co-restriction at the same time. And if we take set X, we can consider all partial functions, partial transformation. So these are all partially defined maps from X to X. So they're defined on subset of X. And this is a restriction semigroup. Domain operation satisfies the axiom. However, the range operation plus does not satisfy the co-restriction axiom. It satisfies only co-Ehresmann. So this semigroup is restriction and co-Ehresmann. And such semigroups will be called range semigroups. So it is a bi-Ehresmann semigroup such that with respect to star operation we have restriction set. And so this terminology stems from category theory and range categories are multi-object and unital generalizations of this notion. They have been considered by Pocket, Go, and Holstrom. So And here I should make a remark that Ehresmann semigroups are called in this work as support categories, so analogs of Ehresmann semigroups, which are unital, it would be monoids, and then multi-objects categories, called support categories, then co-support categories and bi-support categories. Here I'm using terminology which comes from semigroup theory. So Ehresmann semigroups is well-established terminology. Okay, any questions so far? Well, so if you have a restriction semigroup, you may wonder, does it always happen that it admits structure of, say, range semigroup? Does it always admit compatible co-support operation? So what do I mean by compatible co-support operation? Compatible co-support. It just means that if you have, you can see that if with respect to star and plus, you get by Ehresmann semigroup. It is interesting to note that if a restriction semigroup admits a compatible co-support, then it is unique. So let us prove it. So star admits compatible co-support. It is unique. So well, suppose we have two compatible co-supports, and we know one like this and one like this. Yes, and we need to prove that they coincide. Okay, so let me write down like S plus. Well, but we know that S plus S equals to S plus S, right? So instead of S, I just write this, this. And actually, I now use the property that projection can be moved outside the brackets and this. Okay, so all these equalities follow from axioms. And similarly, I can just do this. And because projections commute, I have equality. Yes. And so this coincides with this. Well, it looks very simple, but you might have an impression that we don't use star operation at all, yes? But in fact, we use it. So here, when I say that projections commute, actually, I use the fact that the set of all classes coincides with the set of all stars. So the set of all these classes coincides with the set of all star and coincides with the set of all such classes. And then they get converged. So star is used here. So anyway, compatible co-support is if it exists, then it's unique. Okay. As Julius already told us, natural partial order plays an important role for inverse semigroups and also here for range and restriction semigroups. So by the way, if you have inverse semigroup, then we can indulge it with the structure of bi-restriction semigroup. So we can put S star equals 1S, S plus this S is 1. And so S star is the domain idempotent, S plus is a range idempotent, and then S is the variation become bi-restriction. Also, any monoid is bi-restriction semigroup. To the bi-restriction monoid. You can just put S plus equals S star equals to S of S. So kind of similarly as inverse semigroups can be looked at as common generalization of groups and semilattices. So here, bi-restriction semigroups are common generalization of monoids and semilattices. Okay, so some kind of useful intuition about this object. So anyway, partial order. So if S is restriction, we can put S less than or equal than T if S equals Ts star. And when we think about semigroups of partial maps, it just means that S is a partial map which is a restriction of T to the domain of S. And for co-restriction semigroups, we have dual notion. Okay, compatibility relation. We say that S is compatible with T if S is star equals T star. And two partial maps are compatible when they are eligible to have a join. So when we can put them together and join makes sense, it's again a partial map. So if F and T have a common upper bound, U, then they're automatically compatible. So why is it so? Because let me prove this. So if I write S is star, but I know that S is less than or equal than U, so I can write S like U as star, right? But T as star, instead of T, I put U as star, and now projections compute that I have encoded. So if two elements have common upper bound, they're automatically compatible. But of course, it might happen that they are compatible but don't have upper bound. So about this picture. Restriction semigroup. So we call element S the partial isomorphism. If there is element P, which behaves as if it were inverse of S. So what I mean by this, if this product is S star, and this product is T star. One can prove that if such T exists, then it's necessarily unique. So we denote T as one. And actually, all partial isomorphisms form an inverse semigroup of partial isomorphisms. Which is sub-semigroup of our restriction semigroup S. Well, for example, if you have P partial transformation, then its partial isomorphisms are phi of X, symmetric inverse manner. All partial projections. So here are partially defined injective maps. So maps from subsets of X to X, which are injective. And these are precisely partial isomorphisms. Their inverses are the inverse bijections, the inverse partial bijections. Well, so partial isomorphism is a way to capture partial injective maps, abstract way to capture partial injective maps. But let me consider another example. So let me consider UTX. These are all elements of PTX. It satisfies the following condition: f of x is less than or equal than x. UTX is like, because it's, if I visualize these transformations as 0-1 matrices, these are precisely upper triangular matrices. Well, and if I want to calculate partial isomorphisms here, you see what's the problem? Inverse map of such a map, it doesn't satisfy this property because it will have greater or equal instead of lesser equal. And partial isomorphisms are only diagonal matrices, only projections. And it's not what we expect to get. Partial bijections here, well, there are plenty of partial bijections. So these are injective maps which satisfy this property. It would be 0-1 matrices with at most one in each row and column. So we don't capture partial bijections. And we need another notion which would capture partial bijections in a finer way than partial isomorphisms do. And this motivates the notion of bideterministic maps. Just a second.
Yeah.
Please.
Sorry, but again.
It's just a set.
What's the left?
Well, it can be totally moderate set.
Oh.
Okay, or just finite set from 1 to n if you feel comfortable with it. But I mean, but yes, you could take it. Thank you very much. Yes, actually, to define bideterministic element, I need the setting of range semigroups. So for partial isomorphism, we do restriction semigroups. Let me recall that restriction semigroups have only domain of range, only support. So here, I suppose that we have a range semigroup. So we need also plus operation. And I say that element S is bideterministic if for every projection E, there is projection F such that whenever I have S E, I can move this E to the left-hand side. So from the definition of a restriction semigroup, it follows that I can always move E from left-hand side to right-hand side. But you see, it's hidden here. So E here, right? I can move it to the right-hand side. But if I can do it also from right-hand side to left-hand side, I say that our element is bideterministic. And indeed, via bideterministic elements, in my example, I captured precisely partial injective maps. So bideterministic elements in U, X are precisely injective maps. What we wanted to capture. Well, of course, any partial isomorphism is bideterministic, but not necessarily vice versa. The other way around, in general, it's not true. Every bideterministic partial isomorphism. So it was an introduction to restriction of range semigroups. And I think now I can define Boolean restriction of range semigroups. Before I write down the definition, let us take a convention that we consider semigroups with 0, which is a projection. So for inverse semigroups, 0 is always an idempotent, yes. But here not necessarily. Remember that whenever we have any monoid, we can define all classes and stars to be 1. And then of 0 plus and star is also 1. Strange example, but here we require that 0 is a projection, then 0 star equals 0 plus equals to 0. Or we have only stars and 0 star is 0. Well, so let S be restrictions input, satisfying this condition. And we call it Boolean if the following conditions hold. So first, P of S is a generalized Boolean algebra. So Julius presented to us Boolean algebras, but I will speak about generalized Boolean algebra. So these are Boolean algebras without top element, and instead of negation operation, we have relative complement. And these are locally compact store spaces. Okay, so second axiom is that whenever S is compatible with T, then the adjoint exists in S. Joints of compatible pairs of elements exist. And third condition is right distributivity. So if join exists, then this joint SU, TU exists and we have right distributivity. Well, now I need one more notion, which is called pre-Boolean. So what is the difference from Boolean? Difference is the following. The second axiom is replaced by a weaker axiom. So we have 2 prime, which says if M and T have a common upper bound, then their joint exists. So remember, we said a moment ago that if S and T have upper bound, then they are necessarily compatible. But it's not true that any compatible elements must have an upper bound. So this is indeed a relaxation of 2. Okay, and so this is definition of pre-Boolean. So why do we need this notion? So let's consider very simple example. So if I consider PTX, that is Boolean restriction. A depotence power set of X for Boolean algebra, and it's easy to see that second and third axioms hold. But let me consider symmetric inverse. Well, symmetric inverse semigroup is not Boolean restriction semigroup because, say, second axiom is not satisfied. Let me give you an example on 2 element set. So if I take like 1, 2, it's 1 element, and second is. So these 2 elements are compatible. But their joint does not exist in symmetric inverse semigroup. Because if I take their joint, it will be a transformation which sends 1 and 2 to 1, and it's not partial bijection. So these are 2 partial bijections with their joint existing in partial transformations, but not in partial bijections. Well, so I of X is a Boolean bi-restricted. I didn't write definition of Boolean bi-restriction, so it's pretty similar to this one. Here, instead of compatible, we write bicompatible. If we have bicompatible elements, then they have join. And here, if we take bicompatible elements, they do have join. These 2 elements are not bicompatible. They are compatible with respect to domain, but are not bicompatible because 1 has pre-image 1 and 1 has preimage 2, they differ. So these two elements are compatible, but not bicompatible. So S is not bicompatibility. So this is Boolean bi-restriction, and this is pre-Boolean restriction. Yes, indeed, if two elements have a common upper bound, they do have a joint. These two elements don't have any upper bound, and they don't have joint, no problem. So notion of pre-Boolean is needed to capture both Boolean restriction semigroups and Boolean bi-restriction semigroups. And actually, I will show you very soon an adjunction theorem for pre-Boolean semigroups. And from this adjunction, I will be able to derive two dualities, one for Boolean restriction and one for Boolean bi-restriction. So this is the purpose of pre-Boolean. Okay. These are objects which we work at algebraic side. Maybe I should tell you about morphisms. So we have S, T. So S and T are Boolean restriction semigroups. So what is a morphism? It is 2-1 morphism. So it preserves multiplication and star operation, and its restriction to projection of S is a morphism of generalized Boolean algebra. So these are morphisms. Okay. So from these objects, I will be able to construct ample from restriction and biample from bi-restriction semigroups categories. But let me first introduce these categories and show you construction in the reverse direction. Before I do that, just one more remark. We say that Boolean restriction semigroup has local units if for all S in S, there is a projection E such that E S equals to S. So each element has a left local unit. Note that each element has automatically a right local unit. It's just S star. But left local units don't necessarily exist. I mean, when we don't have plus operation. So we need to impose this. Ample and biample topological category. So these are objects at the topological side of our duality. So what I mean by a topological category? So category consists of discrete category consists of set of arrows, set of objects, unit map from C0 to C1, domain from C1 to C0, similarly range map, and we have multiplication map. C2, C1, where C2 equals fiber product of C1 over C0 and so on. Okay. So now a topological category is an internal category in the category of topological space. So this is topological space, this is topological space, all structure maps are continuous. Okay, topological category. Now, so we say that C is a category if the domain map is a local homeomorphism. An endowment. It's a very strong restriction. It says that space C1 locally, where the map D looks the same as space C0, more or less. Locally, the same as CD. Which property does such category have? So first of all, unit map can be shown similarly as for Egal points, nothing new. But second property is the multiplication map is open. And this was proved by Prisma. So in any Egal category, we have open map U and open map M.
Can I ask a very stupid question? But I don't understand what the multiplication map is. If I think of just categories of objects and multiplication, M is related to conversation.
Yes.
I can go to say it, but
So map M. So it takes two. So here say
down here C2 is C1 times C2.
yes.
C2 is I didn't know it's fine. I thought this was extraordinary. Yeah. The second next.
So some people, you know, that like ER.
Now it's one.
Yeah.
One was two.
Wait. Yes. So the idea is that you take two arrows which
Yeah.
are eligible to have row.
It's fine. It's just one look like two.
Ah,
On
yes.
the very far right. Next.
Yes, yes.
Okay.
I now see. Okay, yes, perfect. Thank you. Yes. So, if we have an entire category, so what can we do? It's actually, there is an easy way to assign a restriction semicolon. But before I do that, let me specialize further to ample category. So, C is ample if C0 is locally compact. So locally compact, how is the totally disconnected space? I just well, equivalently, I can show that this is equivalent to requiring that compact slices form a basis of the topology. So what is a slice? I didn't say. So slice is a subset of our category, which is open, and such that the restriction of the domain map to it is injective. Here I'd like to warn you, slices are sometimes referred to in the literature to what I'm going to call bislices. So bislice will be a subset which is open, such that restriction of the domain map and the range map are injected. But here only domain map. So means that it's open. And restriction of the domain map is injected. So this okay. And we have ample category. Ample means that they have plenty of compact open slices. Okay. So if I have an ample category, maybe I define bi-ample categories immediately after ample. So C is bi-ample. Bi-ample. If it is by et al. By et al means D and R are et al maps. and C0 is locally compact stone space. Or equivalently, biample means that C has a basis C1. I mean, whenever I want C and skip one, I mean arrows. So C1 has a basis of a compact bislice. Okay. So bislice means that this open set target restriction of domain and range mapped to it are injective. Well, maybe some remark. If C is a groupoid, so if I have a groupoid, then G is a tau, if and only if it's by tau. And it's ample, if and only if it's by ample. Okay, that's for groupoids, these notions are inside, but for categories, not in general. Well, so now I start from an ample category. So now C is an ample category. And by CA, it will be the set of what? Of compact slices. Our basis for our topology, similarly as in Julius talk. Yes. Well, the theoretical product of two bisections is again a bisection. Product of open sets is open. Product of compact set is compact because multiplication map is continuous and open, right? And we have well-defined multiplication operations. We have star operation, okay? So what is A star? Well, you take domain of A and then you apply unit map to get back to CA. But I apply unit map, I write 1. Well, and one can show that this is a Boolean restriction sentence. Moreover, it has local units. I'm going to prove this, but perhaps I skip and better tell something else. So one can show that, I mean, this Boolean restriction semigroup always has local units. Well, let's consider at special cases. Look at special cases. So suppose that R is an open vector. So in general, the only restriction on R is that it's continuous. But now let's suppose it's open. Okay. Well, and in this case, I put A plus, where A is element of CA, equals well, U R H. So it's not difficult to see that, well, this set is now open, right? But it's not difficult to see that it's also compact. Because, well, you have dA, you map it to A by inverse to by the restriction to dA, by inverse local homeomorphism, which maps A to dA, so it's again homeomorphism. And then you apply R. And you have map from dA to R of A. And because this map is continuous, it takes compact sets to compact sets. So R of A is compact and open, so it is a compact slice. And in this case, CA with this operation is a Boolean range semigroup. When R is open, we see R at the algebraic side. And it's our co-support operation to us. Moreover, if R is a local homeomorphism, so when our category is in fact biample, so well, we get what we call étale Boolean range semi-group. So what is an étale Boolean range semi-group? It is a special property which says that so étale means that every element of our semigroup, so S is now Boolean range semigroup, if every S in S can be written necessarily compatible of elements S1 to Sn which are bideterministic. So, and in this case, this is indeed the case. And moreover, whenever we are in this setting, then bideterministic elements are precisely a compact by slices. So every compact slice can be written down as a finite join of compact by slices. This is the case. So we restrict it from general situation to R open and then to R local homomorphism. Well, now the next point, which perhaps I mentioned very briefly, it is how to get back. So now we have shown how to come from category to semigroup, right? And now what about the way back? So from Boolean restriction and range semigroups with local units. Two categories. To ample or biample categories. Well, here we use a variation of standard construction known to construct the ample groupoid of inverse semigroup. And here I will use construction of Excel's tight groupoid. So there are various constructions of groupoids like universal groupoid and tight groupoid. And here I need analog of construction of tight groupoid. So in detail. So if S is a Boolean restriction semigroup, you have generalized Boolean algebra of projections. And I can consider its prime spectrum. This is precisely the space of ultrafilters, which Julius told us about, but ultrafilters is the same thing as prime filters, so I will use this terminology. And moreover, I use language of prime characters. So elements of this are prime characters. So these are non-zero maps from PS to generalized Boolean algebra 0, 1. So there is no talk here, right? But it's prohibited that everything goes to 0. So maps are non-zero. And pre-images of 1 are seen as ultrafilters or equivalently as prime filters. So these are prime characters. And so here are maps which preserve operations on generalized Boolean algebra. Okay. Now, so what I want to do with this space, I want to make this space a unit space of a category. So I need to construct arrows. So what I do to construct arrows? Now my semigroup S acts on the space PS head. So if S belongs to S and phi belongs to S head, I require an addition that phi of f star equals to 1, so this whole. I imagine this like this. So here is my phi, and I have I want to define s phi. I want to define s phi. So let me put s phi of E. So E is some projection, yes? So we map from projections to 0, 1. So what I do, I just move this back with S to here and see what phi does on this translated guide. So what I do is phi of E as sum. So multiply, so make S, then I do E, and I take domain of the product. And I see what phi does with this. Now, let me show you where I need the assumption that S has local units. S has local units. I can take E equal to that element such that ES equals this. There is such E, yes? Then I get this product is as phi of S star and know that it's 1. And then I get non-zero map. Because otherwise, if there are no local units, I might get zero map and prime character cannot be zero, right? So I'm trouble. So here it goes smoothly. And I can show that as phi is indeed prime. So actually here it goes under mild assumption that S is pre-Boolean. So here so for pre-Boolean, it works. Already for pre-Boolean. For Boolean, it works. Well, and now I say that two pairs Sx and S phi and T phi are equivalent if phi equals to psi. And so here phi of S star equals to 1, psi T1, T star equals to 1. And if there is U, which is less than equal than S and T, so that such that S phi equals T phi equals U phi. It's an equivalence relation, and the set of equivalence classes is our space of arrows, our category. So we say that S phi is equivalence class of the pair S phi is a germ of S over phi. And we put C bar to be equal the set of the germs. Well, then we can define unit, domain, range, and multiplication maps, which I define as expected. For example, I don't know, domain of F phi, phi, range of F phi equals F phi, etc. And indeed, we get an ample category. Moreover, if our Boolean restriction semigroup admits a structure of a range semigroup, then range map R is open. If it's a tau Boolean range semigroup, then R is a local homeomorphism. So everything is well adjusted to each other. I don't have much time to talk about morphisms. If you have two categories, two ample categories, so S, C, and T, morphisms are cofunctors. Cofunctors from one category to another category. Cofunctors are covariant morphisms. So actually, if I have morphism between Boolean inverse semigroups, then I have covariant functor from them two categories. But beware that if I have a cofunctor, so what is a cofunctor? So we have C0, here we have C0. And when cofunctor points to this direction, it means that there is, here is T0, right? Let me write down C0 here and here T0. Yes, and there is a base map that goes in reverse direction. So cofunctors, well, cofunctors are triples. So it is F and rho. So here mu F, so F is like here. So mu is mu f is an action of C on D0. Yes. And rho is a factor from a partial transformation category, which is identical origins. Actually, I adapted this notion from the notion of cofactor between ample groupoids, which I took from the work by Bass, Excel, and Mayer. Well, and so cofactors very nicely correspond to morphisms of Boolean restriction semigroups, and special kinds of morphisms correspond to special very nice kinds of cofactors. For example, one can define cofactors which are injective on arrows, and this corresponds to so-called weakly mid-preserving morphisms. Surjective on arrows, proper morphisms. Cofactors where action is injective correspond to morphism which map by deterministic elements to bideterministic elements. Injectivity of action holds automatically for groupoids, but should be imposed additionally for categories. Well, and if I have 2 minutes more, I just formulate adjunction and equivalence theory. I have shown you 2 constructions. So, adjunction. We have category of pre-Boolean restriction semigroups. So we have a factor from this category to the category of ample topological categories. Factor C assigns category. And we have factor S back, which assigns to ample category Boolean inverse semigroup, which is in particular also pre-Boolean, right? And these 2 factors establish an adjunction. So, moreover, unit of this adjunction, which is a natural transformation from the identity factor of this category to, so I first do C then N, is described as follows. So its component is at C, S, so I take S. So it maps S to S, and actually it maps each element to. So what is this? It is the set of all germs over S. All germs. And this map is always injected. This map is an isomorphism, even only if our semigroup is in fact Boolean. Well, if I start from a category, go here and go back, I always get an isomorphic category, always. And it shows that this adjunction restricts to the equivalent. So take fixed point equivalence of this adjunction. And we have restrictions here in order to also by C to restrictions in it. So pre-Boolean restrictions in it, and Boolean restrictions. Now, if I look at Boolean by restriction semigroups, Boolean by restriction, Boolean by restriction. The Boolean by restriction semigroup, I assign a bi-ample topological category. It is bi-ample category. And here I can get back from the bi-ample topological category, I get to a town Boolean range semigroup, and then I take bideterministic elements. So I took semigroup, and then I take bideterministic elements. And these are precisely bi-sliced. And I get also as a consequence of the adjunction theorem, which is also equivalence. Well, This covers my result with my closer. This equivalence actually is non-unital generalization of Cocker-Gardner. And we have intermediate equivalences, so this restricts from Boolean restriction to Boolean range to étal Boolean range. So we have actually several equivalences packed in one theorem. Well, and we have some interesting consequences. For example, a Boolean restriction semigroup admits a compatible co-support operation if and only if the map R is open of its topological category. Very nice consequence. And to finish, let me just say that this construction of a category of Jones can be performed for any restriction semigroup with zero, which is a projection. You can construct universal category and type category and more other categories, actually. And this is the subject of future work, and this is just for Boolean now, but we have very nice equivalence categories. For general semigroups, you can construct Booleanization, type Booleanization, some universal objects, you know, and so on, but now, thank you very much.
Yeah, so we already discussed it for trying to get from Boolean to more general structure. But I was just thinking now, actually, like, is there any possibility to just extend a little bit to some kind of distributed lattice, like so you have basic duality that's more general, clonal duality with distributed lattice and no complex. Would there be any possibility to do that here, or?
For duality, duality for distributive inverse semigroups, and
This you advance with this, like
yes,
yeah.
yes, and spectral groupoids, yes, but I think that for Priestley duality there is an obstacle. So I mean, because Priestley duality uses Boolean space and others, and there is an obstacle. I thought from that, but it's a very reasonable question.
Mm-hmm.
Any more questions? I can't tell if there's anyone online, so.